Hello, everyone. So today we're going to be taking a look at graphs that model the velocity of an object. And I just want to remind us or bring back to the forefront of our brain the three functions that deal with position, velocity, and acceleration and the order in which they go. So of course we start with the position function, x of t. And then when we take the derivative of that, we get velocity. And then when we take the derivative of that, we get acceleration. And it goes without saying then, if you go backwards, if you want to start with the acceleration, or if you're given acceleration and you go backwards by taking the integral, you'd get to velocity, and the integral of that would be position. Okay, and we're going to also be talking about some important things like total distance and this word called displacement today. So lots of important information. Let's get started. Okay. Number 1 says, Brina rides her bicycle from her home to Sarah's home, starting at t equals 0 minutes and arriving at Sarah's home at t equals 15. During the time interval 0 less than or equal to t less than or equal to 15, her velocity, v of t, in miles per minute is modeled by the piecewise linear function whose graph is shown below. So this is velocity for Brina's ride to Sarah's house. All right, question A says, and I just want to point out that, of course, velocity is talking about movement. It's talking about if we're moving to the left or to the right, things like that. All right, so question A says, after leaving home, Brina realizes she dropped her calculus homework and she returns to get it. At what time does she return around and go get it? Give a reason for your answer. Okay, so keep in mind they are giving us the velocity graph. This is velocity. And we're talking about she's riding in one direction, she has to stop and turn around to get it, and then she turns back around and goes back towards Sarah's house. So you might be able to look at this graph and just recognize that right away, but if not, if you're having trouble, let's think about making a sign chart. Okay, so if I look at my sign chart from, in this case, 0 to 15 seconds, okay, where is what are our critical values on this sign chart? Well, I know that anytime my velocity graph is equal to 0, that tells me we are at rest. So when velocity is 0, we're at rest. And when is she resting? Well, I can tell that she rests when she starts off at 0, that at t equals 4, and again at t equals 7. Those are the times that she rests. Okay, well, what is happening before and in between and after those times? Well, between 0 and 4, I would say that my velocity graph was positive, telling me that she is moving to the right. Then between 4 and 7, the velocity dips below the x-axis, and so it is negative, telling me that she's moving to the left. And after that, it is again positive above the x-axis, so to the right. What does this sign chart tell me? And like I said, you might have been able to just look at the graph and saw, if velocity is positive, if it's above the x-axis, then we're moving to the right. And then as we dip below the x-axis, we move to the left and again to the right. Okay, so when is she changing directions? Clearly right here at t equals 4. So she turns around at t equals 4. And how do I know that? Because v of t changes sign. All right, let's move on to letter B. Okay, so letter B, we're using the same graph of velocity for Brina, and it says, part B says, find the acceleration, if it exists, of Brina's bicycle at t equals 4, t equals 10, and t equals 12. If it does not exist, explain why, indicate units of measure. Okay, I want to talk about what is the relationship between acceleration and velocity, and hopefully you're screaming out acceleration is the derivative of velocity, or when we're looking at a graph, sometimes we want to think of that as the slope. Okay, and so if I'm looking at specifically these times, so let's talk about acceleration at 4, the acceleration at t equals 4. All right, well, that's right here on the graph. What is the slope of the graph at that time? Well, I'm just looking at what is my rate of change. So here, between this point and this point, I would say that I dropped down 1, 2, 3, 4 and ran forward 2. So negative 4 over 2. Or I could, of course, say that it's just negative 2. Okay, so the slope of that segment where 4 was a part of is negative 2. Okay, so that's the first one. The second one is acceleration at 10. All right, we'll take a look at the graph at 10. What are we noticing? We're noticing that we're at a kink. Okay, and if you remember, kinks are not differentiable. You cannot take the derivative, therefore you can't find the slope at that point. Why is that? Well, because if you think about it, the slope is changing there. Okay, it was one thing between 5 and 10, and then it's another thing between 10 and 13, but what is it right at 10? Well, we'd say that it does not exist. And so we are going to go ahead and say does not exist and tell why. So it says if it does not exist, explain why. Well, we can't just say there's a kink in the graph. So we have to be a little bit more mathematically technical than that. And we're actually going to use limits to help us explain that. So we're going to say that the limit as t is approaching 10 from the left of what? Well, of the slope of velocity is not equal to the limit as t is approaching 10 from the right of the slope of velocity. Okay, so we're just saying that the slopes of these graphs from the left and from the right is not the same. Therefore, the limit doesn't exist. Therefore, acceleration, the derivative in itself does not exist. All right, the last one is a of 12. Okay, so now I'm looking at 12. What is the slope at 12? And hopefully you can easily look at that and tell me that it's 0. Okay, we are not done with that question yet, but before we move on, I want to make sure we get a couple formulas in our notebook that are really important. And I'm sure you've heard these things before if you're in physics. There's this idea of total distance and then this idea of displacement. To highlight the difference, I'm just going to kind of show you a little illustration. So say we have someone who's walking, and we're going to say that they are walking to the right. Let's go with 2 miles. Then they turn around and I don't know, they want to go backwards and go back to a friend's house that was a half a mile back. So they go backwards a half a mile. So I'm going to say negative 0.5. Then they turn back around and continue on the journey that they were going on. And so from that, they go another, we'll say 1.5 miles. All right. Well, there's two different concepts here. There's the idea of total distance and the idea of displacement. Total distance takes into account every single mile that this person walked. So for total distance, I'm going to say that this person walked 2 miles forward, half a mile back. It doesn't matter that it was back, going in the backwards direction, still walked that, and then went ahead and walked another 1.5 miles forward. So ends up with 4 miles. Displacement, okay, is different. That is more the overall distance that she traveled from starting to finishing. And so what's happening here is you're actually going to take into account the negatives. Whereas for total distance, notice that I did not take into account negative 0.5. I included that as a positive 0.5. So for displacement, I'm going to say 2 minus 0.5 plus 1.5. And what ends up happening if you look at my illustration up here is that 0.5 miles that she overlapped, that gets taken out. And so all that we care about is the 2 miles, and then even though she goes back and then comes back forward again, that we're going to take out of our equation and just pick back up from where she left off before she made her initial turn. And so we end up here with 3 miles. So two very different answers, and which is why it's very important that you pay attention to the word and the wording that they're giving you. Okay, so when they're asking us for total distance traveled, there is a formula that we are going to use. So total distance is equal to the integral from A to B, and that would be your starting to your ending time of the absolute value of v of t dt. And it should make sense that it's absolute value like we just talked about because of that positive, or turning everything to positive. It doesn't matter if she's going backwards or forwards, it's still distance that she's traveling. As opposed to displacement, and they might word this lots of different ways, so you're going to have to understand the concept. The displacement formula is the integral from a to b of v of t dt. So here, like we saw in our example, the negative is taken into account, and it's more just the distance that overall she covered as opposed to the distance she traveled. All right, so let's move on and see this application in this problem with Brina. All right, so this question continues on, but it introduces a new character and a new scenario. So it says, suppose Alvin starts riding his skateboard from his home to Sarah's home at t equals 0 minutes, arriving at Sarah's home at t equals 16. During the interval 0 less than or equal to t less than or equal to 16, his velocity in miles per minute is modeled by the velocity function v of t equals 1/20th square root of t. All right, the first question is, who traveled farther, Brina or Alvin? Show the work that leads to your answer. Okay, so who traveled farther is talking about their total travel, so their total distance. So I have to look first at Brina and find out her total distance from the graph, and then at Alvin and find out his total distance given the function, the velocity function that I'm given there. All right, so let's first of all look at her graph. Okay, so for Brina, I'm going to go ahead and do my total distance is the integral from a to b of the absolute value of the velocity function. So this is the velocity function. If I want the integral of it, I'm going to find the area under the curve. Okay, so what I would like you to do is go ahead and pause the video and find the areas underneath the curve for each of these different regions. So I would say you can do this triangle here, of course this triangle here between 4 and 7, and then you might want to split this big trapezoid up a little bit, especially given our heights over here are not counting by ones, we're counting by point ones. And so that just might make it a little bit easier to look at this as a triangle, a square, and then another triangle. All right, go ahead and pause the video and let's get our areas on our graph. Okay, so let's go ahead and compare our areas. From 0 to 4, I have a triangle of 0.4. Between 4 and 7, it's 0.3, but because it's below, I made it negative 0.3. And then from 7 to 10, it was 3 times 0.3, which was 0.9. Divided by 2 is 0.45. My square there is 3 times 0.3, so 0.9. And then this other triangle, 0.3. All right, so if I'm talking about the total distance for Brina, that means I am going to go ahead and do the absolute value of each of these areas. So I'd be 0.4 plus 0.3 plus 0.45 plus 0.9 and plus 0.3. All right, so when I add that up, let's see here, I get, I think, 2.35. Okay, and that is measured in, miles. All right, so that's Brina. Now, if I want to go ahead and find Alvin and his total distance, okay, well, his total distance is from a function. So I'm going to do the same thing, the integral from, okay, so Alvin's time was from 0 to 16, so this should be 0 to 16, whereas Brina's time was 0 to 15 according to the graph. Oh, so this should have been 0 and 15 here. We know our A and our B, so I should have filled those in. Sorry about that. Okay, so the integral from 0 to 16 of the velocity function for Alvin is 1/20th, and I'm just going to write that as t to the 1/2. All right, so I'm going to go ahead and take that integral, so pull out the 1/20th. The integral of t to the 1/2 would be t to the 3/2 divided by 3/2, or times 2/3. And of course that'd be from 0 to 16. All right, so kind of simplifying this, my 2 would go in my 20 10 times. So I get 1/30th, and then I have 16 to the 3/2 minus 0 to the 3/2. Okay, so that would be 1/30th. Let's see here, 16 to the 3/2 is the square root of 16 is 4, cubed is 64, and then obviously minus 0. So that's 64 over 30. And so if I calculate that, I do get 2.13 miles. Okay, so clearly who traveled furthest? or who traveled the most distance would definitely be Brina. Okay, part D of this question says, who lives farther from Sarah's home? Who lives farther from Sarah's home? Show the work that leads your answer. So now we're not talking about the distance that the actual person traveled. It's whose house is actually further from Sarah's house. So this is displacement. This is talking about the placement of Brina's home compared to Sarah's home and Alvin's home compared to Sarah's home. Not the distance that they traveled, but the actual placement of their homes. So this is displacement. So if I bring back up Brina's graph, okay, so this was the graph, and when we did total distance, we had to do absolute value. But for displacement, okay, I'm going to go ahead and just add for Brina. I'm just going to add the numbers exactly as I see them. So I would have 0.4 plus negative 0.3 plus 0.45 plus 0.9 and plus 0.3. Okay, so that sum gives me a total of 1.75 miles. So that tells me that Brina's house is actually 1.7 miles from Sarah's house. All right, what about Alvin? Well, it didn't mention anything about Alvin taking a detour or turning around. We are going to assume that Alvin traveled straight from his house to Sarah's house. And so that 2.13 miles that I got earlier, we're going to go ahead and apply that here. So overall, I'd be able to conclude then that Alvin lives further from Sarah. All right, let's go on to another question. Good job. Okay, so our second question here says a squirrel starts from building A at time t equals 0 and travels along a straight horizontal wire connected to building B. From time 0 to 18, the squirrel's velocity is modeled by the piecewise linear function defined by the graph above. So again, this graph is velocity. At what times in the interval 0 to 18, if any, does the squirrel change direction? Give a reason for your answer. So again, talked about this last time. If the velocity graph is above the x-axis, that means that the squirrel is moving in one direction, to the right. As it dips below the x-axis, that's when it's moving to the left. And then again above would be to the right. And so I would be able to say that there are two times. Time t equals 9 and t equals 15. So change direction at t equals 9 and t equals 15. And why? Because v of t changes sign. All right, let's go ahead and move on to part B. At what time in the interval 0 to 18 is the squirrel farthest from building A? How far from building A is the squirrel at that time? Farthest from building A, that sounds like an absolute maximum. Okay, what am I finding the absolute maximum of? Well, it looks like I'm finding the absolute maximum of the squirrel's position. So if I want the maximum of the position, that would be the derivative of the position. Remember, the function that they're giving us here is velocity, which is the derivative of the position function. Okay, so to do absolute maximum, I'm going to find my critical values, which in this case would be when the derivative of the position was equal to 0 or when v of t is equal to 0. So when does that happen? Well, that's at t equals 0, 9, 15, and that's it. So those are my times that I have to test on a closed interval test for absolute maximum, along with my 0 and my 18. So I'm going to go ahead and set up a closed interval test. And what am I doing here? Well, this is my time, and these are my positions. How do I get from velocity to position? I do the integral. Okay, this is equal to the integral from A to B of my velocity function. All right, so what are my different times? Well, I have time 0, 9, 15, and 18. So I have to find all of these different, what his position is at all of these different times using my graph. So I want you to pause, go ahead and find some of these different areas under the curve, and then we're going to go from there. Okay, so let's go ahead and find the squirrel's position at each of these different times. So the easiest one, the first one, is obviously 0 is going to be 0. At time 0, he hasn't moved at all, so his position is still at 0. All right, what about 9? So I can see that the area under the curve, the integral of the velocity function, is 140 between 0 and 9. So that's my first one. All right, 15. Well, now I'm going all the way. So that's 140 positive minus the 50, and so 90. And then the last one, at time t equals 18, well, now it's that 140 minus the 50 plus 25, and so I end up with 115. And so which of those definitely is the largest, the absolute maximum? I would definitely say this point right here. So I could say the squirrel is furthest from building at t equals 9 seconds and distance equals 140. And they don't give us a unit measure for the distance, and so I'm just going to go ahead and say distance of 140. All right, let's move on to part C. Okay, part C says find the total distance the squirrel travels during the time 0 to 18. So total distance is that concept that we talked about last time. That's the absolute value. Very different. So total distance here is equal to the integral from 0 to 18 of the absolute value of velocity dt. All right, so if I remember here, I had 140, I had negative 50, and I had 25. So when I go ahead and find my total distance here, it'd be 140 plus 50 plus 25. So I would get a total distance here of 215. All right, so let's go ahead and move on to part D. That was a quick one. Okay, letter D says write expressions for the squirrel's acceleration, a of t, and velocity, v of t, for the time interval 4 to 10. So they specifically want us to zone in on from 4 to 10 on this graph. And we need expressions for acceleration and for velocity. All right, let's start with acceleration. Acceleration, remember, is the what to velocity. And hopefully you're screaming out in your head, oh, that's the derivative of velocity. And if I'm looking at a graph, I'm thinking of derivative as slope. So I can see that over the course of this interval from 4 to 10, I have two different slopes that I'm looking at. So I'm going to kind of have to break this up into a piecewise function. I'm going to have to say that a of t is equal to, okay, so I have this piecewise function, and first I would say that the slope from 4 until, let's see here, 7. So that's the first chunk, and what is the slope of this line? And I think you can say it's definitely 0. And that was for specifically time from 4 is less than t is less than 7. Then between 7 and 10, I now have a new slope. All right, so what is that slope? Well, I'm going to use these 2 points, 7, 20, and 10, negative 10, to calculate that slope. So I'm just going to kind of do that over here, and I would say negative 10 minus 20, change in y, over my change in x is 10 minus 7. So that would be negative 30 over 3, so that would give me a slope of negative 10 from the time interval 7 less than t is less than 10. Okay, so this here is my acceleration expression over this entire interval from 4 to 10. All right, now the problem wants us to come up with one for velocity. So if I want an expression for velocity, again from 4 to 10, I'm going to have to once again break it up into two different expressions. If you think about it, this is the graph of velocity. So how do I write an expression for the graph of velocity? Well, I name its equation. And these are just lines. So I write the equation of the line. So I'm going to say velocity is equal to, again, piecewise. Well, what is the equation of this first line? It's just a horizontal line at 20. So I would say 20, and that was from 4 is less than t is less than 7. All right, now I have this other line from 7 to 10. And what is the equation of that line? All right, well, for that line, I need two things. I need a point and a slope. I already found my slope is -10. And you can use either of those 2 points, or you could use the point in the middle, like 810 on it. All right, so I'll just use the 720. That is a point on the line, so I'm going to use that point, and I'm going to use that slope. So I would say y minus 20 equals -10 t minus 7, which of course would be y is equal to -10 t minus 7 plus 20. So this is the expression for velocity from 7 is less than t is less than 10. So this is my piecewise function that expresses velocity for that graph between 4 and 10. All right, we have gone through a lot tonight. I appreciate you sticking with me. I hope that a lot of this is making sense. It's just applying it to these graphs and again, bringing through the idea of the integrals with the graphs. So a lot of this should be very redundant and very repetitive from things that we've done since the beginning of the year with position, velocity, and acceleration. The new piece, of course, is the distance and the displacement. I hope that you've memorized those formulas and you come to class ready for those. All right, thanks a lot and have a great night.